end of the wire. Another identical wire is attached to the bottom of a load, and another load of 2 kg is attached to lower end of this wire. Compute the longitudinal strain produced in both the wires if the cross-sectional area of the wires is 10⁻⁻⁴ meters square. Now this is unsolved problem from your textbook. It is 9th problem. Now to solve this problem, we will draw the figure first. See, there is ceiling to which one wire is attached, which is steel wire, and a load of 2.5 kg is attached to it. Again, another wire is also joined and a load of 2 kg is attached to it. So let's start solving. Data is mass. First mass we will say M1, it is 2.5 kg. Second mass is M2, which is 2 kg. Then area of the wires are given, which is 10⁻⁻⁴ meters square, and Young's modulus of steel is also given. It is 2 into 10⁻11 Newton per meter square. Actually given value is 20 into 10⁻10, so we can write it as 2 into 10⁻11 Newton per meter square. Now here we have to find strain in the first case. So we will just say strain 1 is how much and strain 2 is how much. Now the formula that we will use here, formula of Young's modulus, FL upon AL. Now let us start solving. So here for first wire, means we are considering the first part of the sum. First wire, the mass is 2.5 plus 2. So we will say 4.5 kg. You can see this wire, it is 2.5 kg mass is had, and below that also 2.5. So we can find, since this is first wire, so this will experience both these two masses. So we will add them. So for that I can find the Young's modulus. So it will be FL upon AL. So directly F is not given. So we will use that mass here. We will multiply it by G. So it will be MGL upon AL. So here remember we have to find out strain, and this strain is definitely longitudinal strain. That means we have to find out the ratio of small l to capital L. So I will take small l and capital L here. So this will come here and this will go down. So, and I will get mg upon ay. So let us substitute the values. My m is 4.5, g is 9.8, area is 10⁻⁻⁴, and y value is 2 into 10⁻11. So on calculation you will get the first strain as it is 2.205 into 10⁻⁻⁶. So you can write strain 1 is equal to 2.205 into 10⁻⁶. Since strain is ratio of similar quantities. No unit is there. Now for the second part, for strain 2, consider the mass. Now you can see this is the second wire. For second wire we have only one mass, that is of 2 kg. So for strain 2, similarly we will write, means we can use this expression as it is. So my M is 2 kg here. So L upon L is equal to mg upon AY. Now here M is 2, G is 9.8, area is 10 raised to minus 4 and Y is 2 into 10 raised to 11. So on calculation you will get the strain 2, as you can see this 2 factor will get cancelled and only tens power we will utilize and value is 9.8. So 9.8 into 10 raised to minus 7 is your answer. So you will write strain 2 is equal to 9.8 into 10 raised to minus 7. Now box your answer, and in the answer you will write it properly. Strain in first case is equal to 2.205 into 10 raised to minus 6, and strain in second case, or you can just write strain for first wire, strain for second wire is equal to 9.8 into 10 raised to minus 7. So in this way this problem is solved. Next example is second example from your textbook. It is unsolved problem. The problem is find the increase in pressure required to decrease the volume of mercury by 0.001%. Bulk modulus is given. Bulk modulus of mercury is equal to 2.8 into 10 raised to 10 Newton per meter square. Now very simple example. Let's start solving. Data is given. Here the percentage decrease means change in the volume is given. So delta V is 0.001%. So we will have delta V upon V is equal to 0.001 upon 100. Means change is taken in percentage, so definitely it is related to original volume. So that's why delta V upon V is 0.001 upon 100. So it is 10 raised to minus 5. Now K value is given, bulk modulus, and it is 2.8 into 10 raised to 10 Newton per meter square. Now we have to find change in pressure. That is, we have to find delta P is equal to how much. Now the formula we will use here. Formula is a formula of K, that is bulk modulus. So it is V into dP delta P upon delta V. So formula that we will use here is K is equal to V into delta P upon delta V. Now let's start solving. So solution, very simple. Rewrite the formula. Now here we want delta P, so that's why I will take delta P here. So delta P is equal to K into delta V upon V. Now we will substitute the values here. So delta P is equal to, now K is 2.8 into 10 raised to 10 and delta V upon V is 10 raised to minus 5. So delta P will be just 2.8 will be as it is, 10 raised to 10 and minus 5. So it will get minus, we subtracted 10 raised to 10 minus 5. So it is 10 raised to 5 and unit is Newton per meter square. Now this is your answer. Box it. And mention it properly that the change in the pressure is equal to 2.8 into 10 raised to 5 Newton per meter square. Now here is our next example. It is 6th example from textbook. The example is a solid brass sphere of volume 0.305 meters cube is dropped in ocean where water pressure is 2 into 10 raised to 7 Newton per meter square. If bulk modulus of the liquid is 6.1 into 10 raised to 10 Newton per meter square, what is the change in volume of the sphere? This is similar example, but the thing is situation is different. Now here we are taking a solid brass which have some volume and we are dropping that into the ocean. So let us write down the data here. Now volume of the brass is given, a brass sphere is given, it is 0.305 meter cube. Then the change in pressure, that is where water pressure is given, that means it is a pressure that will be applied on that solid brass sphere. So delta P is given and it is 2 into 10 raised to 7 Newton per meter square. Then K value, that is modulus of liquid, bulk modulus of the liquid is given. So it is 6.1 into 10 raised to 10 Newton per meter square. And we have to find, it is asked what is the change in volume of the sphere. So it is delta V. Now formula we will use here, similar formula that we had used in previous problem. K is equal to V into delta P upon delta V. So let's start solving. So here is your solution. Now we have to find out delta V. That's why we will take delta V here. So delta V is equal to V into delta P upon K. I just interchanged the sign. So delta V is equal to V is 0.305. Then delta P is 2 into 10 raised to 7 and K value is 6.1 into 10 raised to 10. Now multiply these two, 2 into 0.305 and divide it by 6.1 and accordingly calculate for powers of 10. So on calculation you will get delta V is equal to 10 raised to minus 4 meter cube. So this is your answer, and in the answer you will mention it properly. Change in volume of sphere is equal to 10 raised to minus 4 meter cube. So in this way you have to write your answer. Now we will move towards our next example. It is third example from your textbook. The example is a copper metal cube has each side of length 1 meter. The bottom edge of the cube is fixed and the tangential force which is 4.2 into 10 raised to 8 Newton is applied at the top of the surface. Calculate lateral displacement of top if modulus of rigidity of copper is 14 into 10 raised to 10 Newton per meter square. Now you can see this example is based on the lateral displacement that we had considered in three concepts: shearing stress, shearing strain, and also in Poisson's ratio concept. Now here we will solve this. So let us write down data. Now the given things are, you have that cube, so for which the sides are given. So let us write down the data. Here length is height of the cube, so it is 1 meter. Then force applied, lateral force applied is given. So F is equal to 4.2 into 10 raised to 8 Newton. Then the modulus of rigidity is given here. So it is N is equal to 1.4 into, it is not N, it is. Now let us move towards third example. Means it is third example from your textbook. The problem is a copper metal cube has each side of length 1 meter. The bottom edge of the cube is fixed and tangential force 4.2 into 10 raised to 8 is applied to the surface. Calculate lateral displacement of the top if modulus of rigidity of the copper is 14 into 10 raised to 10 Newton per meter square. Now you can see this problem is based on the Poisson's ratio, or means we can say shearing stress or shearing strain, in which we had applied tangential force on a cube. So let us write down the data here. You can see the length is given, so which is height of the cube, as the cubes have all sides equal. So we will write here L is equal to H, which is given as 1 meter. Then force applied is given, so F is equal to 4.2 into 10 raised to 8 Newton. Then the modulus of rigidity is given, so it is eta is equal to 1.4 into 10 raised to 11 Newton per meter square. Now we have to find here lateral displacement. So we will say we have to find out the x value. So formula that we will use here, it is formula of modulus of rigidity. Eta is equal to F into H upon A into X, where F is force, H is height of the cube, A is area, and X is the lateral displacement. So let's start solving. Here we will rewrite this formula according to our need. Here we have to find x. So from formula, x will be, I will take x this side and eta this side. So it will be f into h upon a into eta. So let us substitute the values. So here f is 4.2 into 10 raised to 8 Newton. Then h is 1 meter. Now area, it will be length square. So 1 into 1, and eta is given 1.4 into 10 raised to 11 Newton per meter square. So let us do the calculation. So after calculating, you will get x as 3 millimeter. So in the answer you will mention that lateral displacement is equal to, here I am writing, lateral displacement is 3 millimeter. So this is your answer. Now let us move towards our next example, which is fourth example from your textbook. A copper wire 4 meter long has a diameter of 1 millimeter. If a load of 10 kg weight is attached to other end, what extension is produced if Poisson's ratio is 0.26? What is lateral compression produced in it, where the modulus, Young's modulus for copper wire is given, which is 12.5 into 10 raised to 10 Newton per meter square. Now here you can see they are using one wire for which we have Young's modulus, means we have to deal with the first part of our chapter, that means which is related to length, calculating its Poisson's ratio, Young's modulus and all. So let us have a look. Now let us move towards our next example. It is fourth example from your textbook, unsolved example. Example is a copper wire 4 meter long has a diameter of 1 millimeter. If a load of 10 kg weight is attached at other end, what extension is produced if Poisson's ratio is 0.26? What is lateral compression produced in it, where Young's modulus for copper wire is given 12.5 into 10 raised to 10 Newton per meter square. Now this is simple experiment. We have one copper wire, they are applying some load, so extension is produced in the wire, we have to find out that, and also the change in its area we have to find. So let us write down the data here. Now length of the wire is given, so it is L is equal to 4 meter. Then D, that means its diameter is also given, so D is equal to 1 millimeter. Now the radius we will find from this diameter, so R is equal to D upon 2. So 1 upon 2, so it is 0.5, it will be 0.5. Achha, this was the in millimeter, so it will be also in millimeter. Now here we will convert this into meter, so this will become 0.5 into 10 raised to minus 3 meter. So we got the radius. Now load is applied, it is given in the form of weight, it is 10 kg weight, so that means to convert it into Newton we have to multiply it by G, acceleration due to gravity, so 10 into 9.8 Newton is applied load here. Poisson's ratio is also given, it is sigma, so it is 0.26, and also we have Young's modulus for copper wire, it is 12.5 into 10 raised to 10 Newton per meter square. Now the formula we will use here. Formula of Young's modulus, y is equal to F L upon AL, small al. Then the second formula that we will use, it is formula of Poisson's ratio, which is sigma is equal to L into delta D upon small l into D, where delta D is change in diameter, D is original diameter and small l is extension. Now by using these two formula, we will start solving the example. So I will solve here. Solution. Firstly, we will find the extension produced in the wire which is asked by using the first formula of Young's modulus. So from this formula I can write expression for small l. So it will be FL upon AY. So now it will be FL upon, we don't know the area, so it will be pi r square into y. So let's substitute the values. Now your force is 10 into 9.8, length of the wire is 4 meter and value of pi, it is 3.142. Then r square, radius we have calculated, it is 0.5 into 10 raised to minus 3 the square, and also the we have to substitute the value of Young's modulus, so which is 12.5 into 10 raised to 10. So let us calculate this. You can calculate this using log table. So after calculating, you will get the value of L as 3.994 into 10 raised to minus 3 meter. So this is your first answer. Box this. Now we have to use Poisson's ratio formula to find out change in its diameter. So sigma is equal to L, means I can rewrite this formula like this, L upon small l into delta D upon D. So here we have to find out delta D. So I will rearrange this formula accordingly. So delta D is equal to, you will get sigma D into small l upon capital L. So let us substitute the values here. So delta D is equal to 0.26 into capital D is 1 into 10 raised to minus 3. Here you can see diameter was given, it was 1 millimeter. So I am converting it into meter by multiplying it by 10 raised to minus 3. Then small l that we have calculated now, 3.994 into 10 raised to minus 3 upon the value of L, that is 4 meter. So you will calculate this, and after calculation we will get the answer 2.596 into 10 raised to minus 7 meter. So this is the change in the diameter of the wire. So in the millimeter we can also write 2.596 into 10 raised to minus 4 millimeter. So box this answer. and while writing your answer, mention it properly. So here I will write answer for you. How to write the answer? Let's see. Extension produced in the wire is equal to 3.994 millimeter. Here I am writing it into millimeter. And secondly, the change in its diameter, change in diameter is equal to 2.596 into 10 raised to minus 4 millimeter. So in this way you have to mention your answer properly. Next example is 15th example from your textbook. Now the example is a load of 1 kg produces a certain extension in the wire of length 3 meter and radius 5 into 10 raised to minus 4 meter. How much will be the lateral strain produced in the wire? Now this is also simple example. Here you have one wire and load is applied to it. The length and radius of the wire are given here, and also the Young's modulus is also given. So I am writing here the data. Firstly, the mass, means the load which is producing the extension, is 1 kg. So M is equal to 1 kg. Then we need here gravitation, means acceleration due to gravity, to find out the applied force, that means M into G. So here I have written G is equal to 9.8 meter per second square. Radius of the wire is given, which is 5 into 10 raised to minus 4 meter. Then Young's modulus of the wire is given. It is 7.48 into 10 raised to 10 Newton per meter square. Then sigma is also given here. So it is 0.291. And we have to find here lateral strain. Then we will use the formula, obviously the formula, that is lateral strain is equal to formula of Poisson's ratio. Lateral strain is equal to sigma into longitudinal strain. Now let us have a look how to solve this. So solution. Now longitudinal strain we have to calculate here. Longitudinal strain, you know, it is, means if we are considering Young's modulus here, it will be F upon AY if you remember, Young's modulus, means formula of Y was, it was F into capital L upon A into small l. Now here we are finding longitudinal strain, which is small l upon capital L. So from that particular formula we will write expression for small l upon capital L directly as longitudinal strain is equal to F upon AY. But here force directly is not given, so we will write here M into G. Area is also not given, so we will write it for pi r square into Y as it is. So now the formula for lateral strain will be sigma into this formula. So I will write it here so you can see. Lateral strain sigma into mg upon pi r square into y. So I'm writing in short form just LS, that is lateral strain here. So let us substitute the value. Mass is 1, G is 9.8 upon pi is 3.142 into r square, that is square of radius, which is 5 into 10 raised to minus 4 square into the value of y, which is given 7.48 into 10 raised to 10. Also in the numerator I will substitute the value of sigma as 0.291. So on calculation you will do the calculation and the answer you will get here is in the form of points obviously. So it is 4.856 into 10 raised to minus 5. Box your answer and write down answer properly. As I mentioned earlier for last problem, lateral strain produced in the wire is 4.856 into 10 raised to minus 5. Now here we don't have unit since it is strain, that is ratio of similar quantities, that's why there is no unit. So now let us move towards our next example. So this is the 16th example from your textbook. The example is a steel wire of length 7 meter and cross section 1 millimeter square is hung from a rigid support with a still weight of volume 1000 cc, that is cubic centimeter, hanging from the other end. Find the decrease in the length of the wire when still weight is completely immersed in water. Now this is a little bit complicated example, means they have just rotated it. We will solve it step by step so we will get answer properly. Now let us write down data first. Length is equal to, length of the wire is 7 meter. Area is given 1 millimeter square. So that will be 10 raised to minus 6 meter square. Means we converted it into from millimeter to meter. Then volume is given. It is 1000 cc. So that means centimeter cube. So again we will convert it into meter cube. So it will be 1000 into 10 raised to minus 6 meter cube. So which is 10 raised to minus 3 meter cube. Now the rho value for water is given. So we will write it here. It is 1 gram per centimeter cube. Density, it is density of water. So it is given in the form of grams. So we will convert it into kg per meter cube. It is gram per centimeter cube. We will convert it into kg per meter cube. So that will be 10 raised to 3 kg per meter cube. G value we will get now Y value is also given. It is 2 into 10 raised to 11 Newton per meter square. Now here we have to find change in length. So let us write down the formula. Formula is Y is equal to FL from Young's modulus. Now from this formula we can find extension in the wire. So let us solve. So solution from this formula, L is equal to FL upon AY. Let us substitute the values. Now here we have two conditions. When wire is suspended, steel weight is immersed, and secondly it is immersed in water. So now we can rewrite this expression for length, that is small l, from the Young's formula. So Young's modulus formula. So this is FL upon AY. Now here we have two conditions. Firstly, the steel weight is in air, and secondly steel weight is immersed in water. So for two particular cases we will have the formula in two ways. Means we will write, for first case we will write L1 is equal to F1 into L upon AY, and for the second case, when it is suspended inside the water, L2 F2 into L upon AY. Now we are taking same length, same material, that's why the area, length and its Young's modulus will not change. So let us see how to solve this. Now we have written conditions for L1. Now L1 is length when the steel wire is in air, and L2 is the length when it is immersed inside the water. So we will, let's see, divide the expression to first find out the change in length, or we can find the change in the force applied also. Now here we will see. Now so from the Young's formula I have written expression for L1 and L2. Here L1 is length when steel weight is hanging in air, and L2 is length when the same weight is immersed inside the water. Now here we have to find delta L. That means we have to find change in length L1 minus L2. So for that we will subtract these two equations. All the values are similar, L, A, Y, three values are similar, but forces applied here we don't know. So we have to find out first the difference between the two forces, that is from F1 to F2. We should subtract it, and we have to find the expression for F1 minus F2. So F1 minus F2 is here upthrust due to water. Definitely the weight was air, means weight was hanging in air firstly, then it is immersed in water. So the force which will act on that weight will be upthrust due to water. So now if you remember the 9th standard, the upthrust we will calculate by using the formula here. F1 minus F2 is upthrust due to water. So definitely this upthrust is proportional to firstly volume of that steel weight, then density of water, and also the acceleration due to gravity. So this will be V rho into G. So this is the expression for upthrust, V into rho into G. So we will substitute here. So we will subtract equation 1 and 2, or directly I can write L1 minus L2 is equal to F1 minus F2, and all the other terms we will take constant. So L upon A into Y. So the expression will become V rho G L upon AY. So substitute the values. Now V we have 10 raised to minus 3. Rho we have, it is 10 raised to 3. Then G also we have, it is 9.8, and value of L is 7 upon area, it will be pi r square, or I guess we have the area, yeah, it is 10 raised to minus 6 meter square. It is given directly, and the value of y 2 into 10 raised to 11. So L1 minus L2 is actually change in length, so it is delta L. So by calculating these particular values, you will get the answer as 0.343 millimeter. Means the actual answer will be 34.3 into 10 raised to minus 5 meter. So that meter I am converting it into millimeter. So this is your answer. It is delta L is equal to 0.343 millimeter. So we will mention that change in length is equal to 0.343 millimeter. Next example is 11th example from your textbook. The example is an uniform steel rod of 5 square millimeter cross section is heated from 0 degree to 25 degrees Celsius. Find the force which must be exerted to prevent it from expanding. Also find energy stored per unit volume. Now alpha for steel is given as 12 into 10 raised to minus 6 degrees Celsius, and Young's modulus for steel is given 20 into 10 raised to 10 Newton per meter square. Now this example is based on elasticity, as well as, if you remember, it is based on the heat concept. Here expansion concept is mentioned. So let us see how to solve this. Firstly, we will write data here. Now area is given. It is 5 millimeters square. So we will convert it into meter square. So it will be 5 into 10 raised to minus 6 meter square. Then temperature difference is given. That means they are heating that particular thing, that rod, from 0 to 25. So delta theta we can write. Delta theta is final temperature minus initial temperature. So 25 minus 0, so which is 25 degrees Celsius. Then the alpha value given, it is 12 into 10 raised to minus 6 per degree Celsius. Then y is also given, Young's modulus 20 into 10 raised to 10 Newton per meter square. Now here we have to find the force and strain energy per unit volume. So let us write to find force and also U, that is strain energy per unit volume. Now let us write down the formula. If you remember, in our theory we had derived expression for linear expansion and Young's modulus, that I am writing here. It was in the form of force. So F is equal to y alpha delta theta into area. So this was our first formula, and the formula of strain energy. So it is half into stress square upon y, that is Young's modulus. Now let's start solving. Solution. We will find force first. So F is equal to, here it is given as, can see 20 into 10 raised to 10, means we will substitute the values directly in the formula. If you want, I will rewrite the formula. It was F is equal to Y alpha delta theta into A. Now I am substituting the value. So Y is 20 into 10 raised to 10. Alpha is, you can see, 12 into 10 raised to minus 6. Then the value of delta theta is 25 and area is given as, I am writing below, 5 into 10 raised to minus 6. So it is just multiplication, simple multiplication. So after calculating these values, you will get F is equal to 300 Newton. So this is our first answer. Now let us find out strain energy per unit volume. So it is 1 upon 2y. Here from this formula I can write 1 upon 2y and stress square. But we don't know the exact stress. But as you know, stress is force upon area. So I will write F upon A, the square, because it is stress square. So U is equal to 1 upon 2 into the value of Y, that is 20 into 10 raised to 10. In the bracket, force we have calculated just now, it is 300 upon area is 5 into 10 raised to minus 6, square of whole quantity. Now after calculating this value, you will get your answer as, it is 9000 joules per meter cube. So you will write it properly. Write in the answer, the force applied is equal to 300 Newton and strain energy per unit volume is 9000 joules per meter cube. Now this was simple calculation. You can see 300 square will be, it will be 90000. Then it is 2 to the 4, means 40 into 5. So it will be 100 something and all the powers will get cancelled and you will get 9000 joules per meter cube. Now next example is 13th example. Example is a uniform steel wire of length 3 meter and area of cross section 2 millimeter square is extended through 3 millimeter. Calculate the energy stored in the wire if elastic limit is not exceeded. And the Young's modulus for steel, it is given as 2 into 10 raised to 10 Newton per meter square. Now let us write down data first. Here the length of the wire is given 3 meter. Area is also given. It is 2 millimeter square. So it will be 2 into 10 raised to minus 6 meter square. Then extension in the wire is given. Again it is in the form of millimeter. It is 3 millimeter. So it will be 3 into 10 raised to minus 3 meter. Then Young's modulus for steel is given. It is 2 into 10 raised to 10 Newton per meter square. Now here we have to find strain energy, that is U. Now formula that we will use here, it is said that, as you know, this energy means work done on the wire or by the wire. Since we are loading the load here on the wire, so work is done by the wire. So this work is stored in the form of energy only. So here we will write the formula of work, which is half into force into extension. So again one more formula that we will use here, formula of Young's modulus, FL upon AL, where A into L is smaller. So let us start solving. Now solution. Now here to find out, we are using second formula to find out F in the first formula. So from second formula I can write expression of our F as YAL upon capital L. So we will substitute this value of F in our first formula. So W is equal to half, it was F, so YAL upon capital L into our small l. So let us substitute the values. So W is equal to half into Y is 2 into 10 raised to 10. Then area is given 2 into 20 raised to minus 6. Now here we have L 2 times, so I will just square it. So 3 into 10 raised to minus 3 square upon capital L. So value of capital L is, you can see, 3 meter. It is in meter only. So 3 here. So you will calculate these, carry on the calculation, and you will get W as 0.06 joules. So lastly you can write work stored in the form of energy in the wire is equal to 0.06 joules. Now let us move towards our next example. It is fifth example from your textbook. Example is, calculate the work done in stretching a steel wire of length 2 meter and cross sectional area 0.0225 millimeter square when a load of 100 Newton is applied slowly to its free end. Young's modulus of the steel is 2 into 10 raised to 10 Newton per meter square. Now this is exactly similar problem to the previous one. So let us write down data here. Here length of the wire is given as 2 meter. Then its cross sectional area is also given. It is 0.0225 millimeter square. So we will convert it into meters. So it will be 2.25 into 10 raised to minus 8 meter square. Now I shifted I shifted the point by 2 digits on right hand side, and accordingly I adjusted the power of 10. Now Young's modulus is also given. It is 2 into 10 raised to 10 Newton per meter square. Here we have to find work done by the load. So we have to find W here. Formula, it is simple formula. W is equal to half F into small l, that is extension in the wire. But here we don't know the value of small l. So to find out the value of small l, we will use the formula of Young's modulus, that is F capital L upon A into small l. So let us start solving. So solution. So from this formula I can have expression for small l. So small l will be F L upon A Y. I just shifted small l here and y here. So this is the formula for small l. Now we will substitute this L in our original formula. So W is equal to half into F into the expression for small l. So it will be F into L upon A into Y. So you can see the formula becomes half into f square L upon A y. So let us substitute the values. Half into, now here the value of force is given as 100. So this will be 100 square into the value of length is 2 upon area, it is 2.25 into 10 raised to minus 8 into the value of the Young's modulus. So which is, it is 2 into 10 raised to 10. Here actually the value of Young's modulus for still is 20 into 10 raised to 10. So we will modify it. So accordingly I will change my power. So after calculation you will get your value of W as 2.222 joules. So this was a simple problem. In the data mentioned force is equal to 100 Newton. So in the answer you will write properly the work done by the load or work done on the wire is equal to 2.222 joules. So this was your last example. So in this way, step by step, we have solved all the examples from your textbook, solved as well as unsolved example. For practice, you can refer other books also like Bangwe and all. So in this way, we should try to solve more and more examples so that we can have more practice.